Okay, so let's just say we want to solve this linear system. Let's say we want to solve. I'll just pick one out of the book here. Okay, so if I want to solve that linear system, we'd call that a 3x3 system, right? It would just a number of variables by the number of equations. And I need to get my calculator set up here. Okay, when you're going to solve these things using a matrix method, using a calculator, you have to always write them in standard form. And you know what that is, right? That just means we're going to have the terms in typically alphabetical order of the variables, the terms in that order on the left side, and then the constant on the right side. Okay, so here's all you do. Right, so if you want to use a calculator to do these, and the nice thing about this, if we had a 2x2 system, you wouldn't even have to bother using a calculator. That'd be easy to do. But when you start getting bigger, fatter linear systems, 3x3, you could even do like a 10x10 this way. And doing that method algebraically might take you, even you guys would take you hours and hours and much confusion and head scratching to do a system like that. But on a calculator with a matrix method, it's very, very simple. All you do is you just go to the matrix screen, so second matrix, and we're going to enter this matrix in what's called enter it as an augmented matrix in echelon form, which just means that we're going to put everything in there, not just a square matrix, but actually it's going to be a rectangular matrix. We're going to add an extra column for the constants on the other side of the equation. So instead of, as you might remember, probably doing this as a 3x3 and a 3x1, we're going to do it as a single matrix as a 3x4. So we'll go over and edit matrix A, and you guys are familiar with, probably have done this before, right on here. So you kind of know your way around the graphing calculator when it comes to this stuff. So we'll edit matrix A, we'll make it a 3x4, oops, 3x4, and it'll build the template for you. And then what are going to be the coefficients in the first row then? Okay, so -2. Why don't you read them to me so I have to look up? -3.
Sorry.
-26. Okay. And you remember that with the calculator, it reads just like a book. So if you enter the numbers in a matrix, you're gonna go from left to right and then down, right? Okay. So next row. 200. Okay. Okay. Next row.
1, 0.
Okay, 0. Good. Where's the 0? Okay, because we're missing a z term, what would the coefficient of z have to be for it to be missing? 0, right? So any missing terms always have 0 coefficients. And then -10. Okay, so we got our 3x4 matrix. Now watch how easy this is. It's really simple. All I've got to do, I'm just going to quit, and I go back to the matrix screen. I scoot over to the math menu, and I'm going to go all the way down to RREF, which is near the bottom. So I'll actually cheat and go up to the bottom of the list. And there it is right there. It's B, RREF. What that stands for is reduced row echelon form. And so what it's going to do, you guys who are all going to go on and take lots of math, when you get to college, you're going to probably take a class, well, not probably, you'll take a class called Linear Algebra and Matrix Theory or some variation on that title. And it's going to talk about how you can do linear algebra like this, where you're using these types of linear systems, where you can use matrices to solve these things. And typically you'll learn all the row operations, the things you can do to a matrix to make it turn from the one that we just entered into the one that we're going to get. Now the calculator's going to do all those operations for you. And I bet you that increasingly, sort of those row operations, those manual row operations kind of become a lost art like the slide rule, because it's so easy to do them on calculators and computers now. But anyway, the calculator's gonna do all these. There's all kinds of rules about what you can do with rows and columns and matrices. You know, you can multiply a row by any constant. You can do all these little rules that you guys don't know yet, but the calculator does. And so when I go RREF, I just have to tell it which matrix we want to reduce. Well, matrix A is the one that we created, so I'll just go back to the matrix menu, call it matrix A, and ask it to do that. Return matrix A, put matrix A in reduced row echelon form. Now, if I hit enter, here's what it's going to do. Look what it does here. Now think what these rows meant. When we put a row into our augmented matrix, it meant the first number was, the first column are the coefficients of x, second column is coefficients of y, third column represents coefficients of z, last column represents the constants, right? So think what this matrix is really saying here. This first row, what does that mean? 1, 0, 0, negative 306. Yeah, it means that. It means 1 times x plus 0y plus 0z. So really just x equals negative 306. How about that? Second row means 1 times y equals 296. And then last column, z equals negative 41 2/3, right? And if I want to make these into fractions, I can, right? I can take this whole thing and just go math, convert to fraction, and look, it'll even turn those into fractions for me if I want it to, right? Okay, now, so here's what you look for with these. You can kind of take this real shortcut. This is really slick. I just look for, if I cover up the third column, or the last column, whatever that is, sorry, the fourth column in this case, if I get what's called an identity matrix, right? If I get a matrix that looks like upper left to bottom right is a descending diagonal of all ones, and everything else is a 0, that's what we call an identity matrix, then that immediately tells me that this is a system with one solution, and these are the values of the variables in that one solution, okay? But you may remember, going back a couple of years here when you're doing this stuff, that it doesn't always work out that way. There's some other possibilities too, right? It's possible that there are many solutions. For example, in a 2x2 linear system with 2 lines, what if the lines overlapped, right? Or if I have a 3x3 system where we're graphing planes, what if the planes intersect at a line, for example? All 3 planes intersect at a line, like the roof and this wall, and say another one that's going up and meeting at that same joint. Those would all be examples where there's not one solution, there are an infinite number of solutions. That's one possibility. And what if everything's parallel? What if nothing ever intersects, so there's no intersection? The inverse method was horrible about that. Remember that you ran into a roadblock when you used the matrices there. The calculator just said something like singular matrix. Remember running into, and then you don't know what it is. Is it many solutions or is it no solutions? The calculator didn't tell you which one it was. This one will. If you get an example that doesn't fit the normal criteria, right? It's not a single solution. All you have to do is cover up everything except the bottom row. If the bottom row is a true statement, in other words, if it's all zeros, and think what that means. 0x plus 0y plus 0z equals, of course, 0. If it's true, how often is a true statement true? Always, right? And so that means there are many solutions, an infinite number of solutions, because it's true all the time. That's the way to remember it. If it's an untrue statement, and typically what it'll say is 0, 0, 0, 1, that's not true. 0x plus 0y plus 0z cannot equal 1. How often is an untrue statement true? Never. There are no solutions in that case. So it actually tells you the collapsed form of those matrices. If it doesn't work, if you don't get a single solution, this way will still tell you what's happened Is it a no solution or a many solution type of answer? That make sense? Okay. So when you do a problem like this one, this is the way you want to do it. Once you get your linear system set up, don't mess around trying to solve that thing by hand. Just throw it in the calculator. Okay? So quickly back to our problem here then. So we can immediately get 3 equations out of this. We really just need one more, right? We really just need one more. And maybe we can even get, if we were doing this one by hand, it'd be kind of a pain to have all of these equations involving A, B, C, and D. That makes it harder to solve. We'd rather have some smaller equations that allow us to maybe find the values of, a couple of these variables, so everything gets easier. Where could we get at least one extra equation that doesn't come just from the values of the coordinates? And suggestion was made, how about the derivatives, right? For example, if I know that there is a relative maximum at 2, 4, right? What does that mean about the derivative?
It's 0.
Okay, well, either it would be 0 or it's undefined, but remember that we're dealing with a polynomial here, right? And so is a polynomial, if I take the derivative of a polynomial, what am I going to get back? A polynomial, just a smaller polynomial, right? And so I know that polynomials are never undefined anywhere, right? As I've said before, polynomials are well behaved. You'll never get an undefined derivative. You only get 0 derivatives. So we know which one it is. So I know that when I take the derivative, it must equal 0 when x equals 2, right? Everybody see that? That's pretty slick. So if we take the derivative then, what are we going to get for a derivative? Let's see, we get f prime of x equals, what's that be, 3, that's a 3 up there. So we're going to get 3ax squared plus 2bx plus c, okay? And we had, the point was 2, 4, right? So then we know that f prime of 2 must equal 0, right? So when I plug 2 in for x, I've got to get 0 there. So I get 3 times a times 2 squared, right, which is what, 12? 12a. 2 times b times 2 would be 4b plus c. So there's a smaller equation, right? How about that? Make sense? And if I did a second derivative, I'd even get a smaller one, right? If I differentiated this again, I'm gonna get a 2-term polynomial, and I know that that would have to equal 0 when x is 3, right? Okay. All right. I think. What else do we have? There's another real tricky one. I think that was the main one. Yeah. All right. Kind of don't have much time left. Do you want to go to the lab, or do you want to just go maybe through a 3-4 problem? 3-4 problem. Okay. Now we started one yesterday. Do we want to finish that one with the trig one? Maurice, which one were you looking at? That was a good one too.
It was 34.
34. Okay. I think it was too.
Was that or 32? Pretty sure it was 32.
No, 35.
It was 32 that we were looking
But 32 is the one that we were looking at in class yesterday. Okay, so I think we had started looking at 33, hadn't we? Which would be real similar. Real similar to 32. I wonder if did I save that one? I hope I did. I think I did. That would have been this guy. Yeah, I'm pretty sure I did. Yeah, this was it. There it is, right? So this is the one we were doing, right? And look what we had done. So we, this, of course, we got into lots of discussions about this, but really what we'd done in terms of the calculus was we had differentiated, right? So we found f prime of x, and we were looking for the critical numbers, right? And I think, let's see, so let me make this a little bigger. Okay, and we were looking for when they're undefined. So we know if this is our derivative right here, we wrote it in terms of sines and cosines, and we got it as this ratio, right? So we got this thing written as the sine of x minus pi halves over cosine squared of x minus pi halves. And so we know then that the derivative is undefined when the denominator equals 0 and equals 0 when the numerator is 0. So it's undefined when cosine of x minus pi halves equals 0, right? Remember this stuff? And we need to find that on our domain, which is for x. Our domain was, in terms of x, was x has to be greater than 0 and less than 4 pi. And we just explored all the options. We just said, what if x minus pi halves, which is creating the angle that we're feeding cosine, well, that wouldn't work when that equals pi halves, because cosine is 0 there. It wouldn't work when all that stuff is equal to 3 halves pi. That's also right. Or, well, I think we said, or 5 halves pi, did we even look at?
Yeah.
I think we did, yeah. We had to. And we, right here, okay, and we looked at all those possibilities. And then we said, okay, well, really, what we could do if we wanted to is we could just set it equal to pi halves plus n pi, where n is some integer. Then if n is 0, it's pi halves. If it's 1, it'd be 3 halves pi. If n were 2, it'd be 5 halves pi, etc. We'll get an answer in terms of n, but we'll only keep the values of n that make our answer true inside our domain, right? And so we solved that equation. We just said pi halves plus n pi. Where did we do that? Next page, I guess? Oh, shoot. Yeah, right there, right? We just set pi halves plus n pi equal to x plus, or x minus pi halves, right? And you see where we get that? Because we're taking the cosine, we called theta x minus pi halves. So that's what we want to know when the value of that equals pi halves, 3 halves pi, 5 halves pi. In other words, pi halves plus n pi. So we're setting these two things equal to each other, right? We want to know when does this angle take on any of these values, because those are the ones where cosine is 0. And we get 0 on the bottom of our derivative, and we get undefined, right? So we solved that. What did we do? We added pi halves to both sides, and then we get x equals pi plus n pi. And we could write that if I factor a pi out. It's just that, isn't it? Right? So for which values would that give us answers inside our domain? Well, we can see that if n is integers, we're just getting back integer values of pi, aren't we? So we'll just keep the ones that are between 0 and 4 pi. So pi and 2 pi and 3 pi, right? And there was our answer. So that's where it's undefined. That's where we left off. Okay. Well, what we didn't do was the other part of the derivative. That's where we left off. We didn't find out where is sine equal to 0, right? Because that's going to be where the numerator of our derivative function is 0. The derivative will take the value of 0, right? So we'd have to solve that problem. Where is sine x minus pi halves equal to 0? Okay. So equals 0 when x minus pi halves equals what? Well, if we look on the unit circle, where is sine equal to 0?
0.
Okay, 0, pi, 2 pi, 3 pi, 4 pi. How can I say all those at once? n pi, right? Where n is just some integer. So x minus pi halves equals n pi. Solve for x. Well, that's just n pi plus pi halves, right? So if we let n, if n's 0, that's just going to give us back pi halves. If n is 1, that's going to give us 3 halves pi, etc., right? So which of those are going to be in our domain between 0 and 4 pi? Pi halves, what? Pi halves, 3 halves pi, 5 halves pi, 7 halves pi?
No, not
7 halves, wouldn't 7 halves be less than, that would be 8 halves, right? 4 pi would? Does that make sense? So I'd have to include 5 halves pi and 7 halves pi, it looks like. So all 4 of those, I got a lot of critical numbers, tons of them. I get all those guys, and we also had pi, 2 pi, and 3 pi. So my table is going to be a mess, right? And that's just for the first derivative. This kind of ugly problem. And we still have to go back and calculate the second derivative. Should have picked a different one. And here's where we have so here's our second derivative, our first derivative, sorry. It's either secant times tangent or it's sine divided by cosine squared. Which one do you want to differentiate in? I mean, they're both pretty ugly. There's a product. The argument there being it's a product. What's the advantage of this one? They're sines and cosines, yeah. Take your pick. Honestly, I'd probably do this one just because it's sines and cosines instead of secants. Every time you take the derivative of a secant or a tangent, it sort of multiplies. Derivative of secant is secant times tangent, right? So, I'd probably do this one, but I might be wrong. I don't know. So let's take this one. So we left off here. So what's my second derivative going to be then? So what's the quotient rule telling me here? Gotta go bottom, right? So a bottom times derivative of the top. So I'm going to get cosine squared x minus pi halves. What's the derivative of sine? Positive cosine. So what's going to happen if I multiply cosine squared times cosine? What's that going to give me? Cosine cubed. Everybody see that? So I'm going to get cosine cubed minus top times derivative of the bottom. So sine of all that stuff. What's the derivative of the bottom? You got to be careful with this, because the part that messes people up on this is that guy. What's the outside layer of this derivative? Is it a cosine or is it a power? Power. Because really, what this is equal to is the quantity cosine of x minus pi halves squared, right? At least in your mind, you always want to think of it that way. Maybe you won't even want to write it down. So the derivative of that is what? 2 times cosine times negative sine. Now, if I multiply negative sine times this term, how can I make this a little easier? What's that going to give us? Positive sine squared. Okay. And then all divided by, what are we going to get on the bottom? Bottom squared, cosine squared would be cosine to the 4th. Okay, that looks pretty bad, but actually this one isn't such, it's not that bad. Did I mess it up?
No.
Okay. So if I factor out a cosine from both of these, right? I could factor a cosine out and cancel it with one on the bottom. Everybody agree? Leave sine squared plus 2 sine squared. I can cancel this guy and make that a cube. Okay, and so that's a little better. Boy, not much, is it? We're not going to finish this one, obviously, but this is going to be a bad one. Because this is going to be a really bad one, because you're going to get so many critical numbers on there. Yeah, it's already a bad one, isn't it? Bad choice. Shouldn't have picked this one. Alrighty. Yours are easier, I promise.